for our octahedral electron domain geometry, we've got, just like all the others, several other molecular geometries that can derive from it. So if you got take away one of our atoms and replace it with a lone pair, you're going to end up with a square pyramidal shape. We're going to remove one of our axials. Because all of these are at 90 degrees, it doesn't matter. Just still think of them as being an axis. That's going to give us a square pyramidal shape. If I take away a second one, I'm going to end up with a square planar shape. So I've got 6 total electron clouds, 4 of them are atoms, it'll be square planar. If I take away another one and I've got 3 electron clouds and 3 atoms, it's going to be a T shape. So let's do some examples. So phosphorus reacts with excess chlorine gas. The compound phosphorus pentachloride is formed. In gaseous and liquid states, this substance consists of phosphorus pentachloride molecules, but in the solid state, it's going to be a 1-to-1 mixture of phosphorus tetrachloride plus ions and phosphorus hexachloride anions. Predict the geometric structures of all 3. Right. So we're going to start off with our molecular structure. First thing we would do is draw the Lewis structure for phosphorus pentachloride. We've got 5 pairs of electrons around the phosphorus atom. We're going to require a trigonal bipyramidal arrangement. Right. When we introduce the chlorines, all of those positions are filled by atoms, and so we've got a trigonal bipyramidal molecule as well as a trigonal bipyramidal electron domain geometry. If we draw the structure for the ion, right, we're going to end up with 5 plus 4 times 7 minus 1, because we've lost 1 for this plus charge, gives us 32 valence electrons. And we're going to draw that Lewis structure to look like this. Right, we're going to put it in the parentheses with a plus charge to indicate it's charged. I've got 4 things, so its electron domain geometry will be tetrahedral. I look at the 4 things that are surrounding my central atom. All of them are atoms, so my molecular geometry and my electron domain geometry are both tetrahedral. Right? If I go to the phosphorus hexachloride minus 1 anion, I'm going to do 5 plus 6 times 7 plus 1 electron for 48 valence electrons. Since our phosphorus is surrounded by 6 pairs of electrons, an octahedral arrangement is required to minimize the repulsions, as shown below in the middle. So we're going to have 1, 2, 3, 4, 5, 6 things around our phosphorus. Right, if I got 6 things around it, I'm going to need this trigonal bipyramidal structure. All 6 things are atoms, so my molecular geometry and my electron domain geometry are both octahedral. So what about if you've got a double bond in there? Well, you're going to treat it exactly like you would any other thing, like a single bond or a lone pair of electrons or a triple bond. So when using the VSEPR model, a double bond is considered as only one effective pair. And 2 pairs involved in the double bond are not going to be independent of each other, and a double bond just acts as one center of electron density that's going to repel other electrons. So you're going to say, yeah, I know there's more than 1 electron involved in the double bond here. We're just going to treat it as 1 electron domain. With molecules that exhibit resonance, any one of the resonance structures can be used to predict its molecular structure using the VSEPR molecule. So let's predict the molecular structure of the sulfur dioxide molecule. Is this molecule expected to have a dipole moment? We'll talk about that in a little bit more, but first we're going to determine the Lewis structure of the SO2 molecule, which is going to have 18 valence electrons. We've got 2 resonance structures that we could generate, one with a double bond to the left and one with a double bond to the right. Right. In our VSEPR model, does it matter whether you've got a double bond or a single bond? No. Right? All it matters is the number of things around that central atom. Here we've got 3 things around that central atom, so our electron domain geometry is going to be trigonal planar. Right? So to determine the molecular structure, we'll count the electron pairs around the sulfur atom. In each of those resonance structures, you've got 1 lone pair, 1 pair in a single bond, and 1 pair in a double bond. You count the double bond as 1 pair. It's going to give you 3 things around that sulfur. You get a trigonal arrangement, trigonal planar arrangement for your electron domains, and it's going to yield a bent or V-shaped molecule when you talk about the molecular geometry. So our molecular geometry, remember, just includes the atoms. Thus, the structure of SO2 molecule is expected to be V-shaped with a 120-degree bond angle, more or less. The molecule will have a dipole moment, as shown below. So what's happening with those, to kind of do it a little bit early, is we've got a polar bond between the sulfur and the oxygen. And we've got a polar bond between this sulfur and this oxygen. And if we add up those unevennesses, right, if we add up those polar bonds as vectors, we'll end up combining them to get a net dipole for the molecule. So we've got a net dipole moment for the whole molecule, not just for those individual polar bonds. Since the molecule is V-shaped, the polar bonds are not canceling each other out. We end up with a net dipole going kind of up through the middle towards those oxygens. Okay. What if you got more than one central atom? Well, the real simple rule is you break it down one step at a time and you walk through each atom and treat it as the central atom and the rest of the stuff as just being one electron domain. So instead of saying, I got an atom over here, you got a group of atoms. So our VSEPR model can accurately determine the structure of complicated molecules such as methanol, right? And this VSEPR model works out, and the valence bond model works out really well for organic molecules, which is why we're teaching it to you. It's not the most sophisticated model out there. It's got some flaws and limitations, but it's really good for doing organic chemistry. And what are most of you going to do next? Organic chemistry. So our Lewis structure for methanol will look like this. We've got a carbon in the middle. It's got 3 hydrogens and then an O and an H on it. Functional groups are something you will learn about, but this OH will travel around together as a part of what makes something an alcohol group. So methanol's got 1 carbon and an OH group. Ethanol is going to have 2 carbons surrounded by enough hydrogens and then an OH group at the end. There are 4 pairs of electrons around the carbon and the oxygen atoms, which give rise to a tetrahedral arrangement. So looking at this carbon is going to be tetrahedral. Right? The space recurrence of the lone pairs are going to kind of distort some of that arrangement. It's not going to be that ideal 109.5 degree angle, but around this carbon, it will be a tetrahedron. Right? So we'll treat the carbon, right, carbon to the hydrogen to the oxygen as being like a tetrahedron. Around the oxygen, we move over and we just treat it as its own central atom. So around this oxygen, it's also going to act like a tetrahedron, right? Because I've got 2 lone pairs, 1, 2, and then 2 single bonds, 1, 2, 3, 4 things around my central atom. So it's going to be a tetrahedron. And in order for us to kind of minimize those distances between or maximize our distances, minimize our repulsion, we're going to kind of stick this hydrogen out to the other side, out to one side. All right, so we're looking at combining really 2 different tetrahedra. The arrangement of the electron pairs around the carbon atom and the atoms in the carbon, and we look at the arrangement of bonding of the lone pairs around the oxygen atom, and that's going to give rise to our overall molecular structure. Let's look at some of the trends here. So bonding pairs are going to be shared between 2 nuclei. Electrons can be close to either nucleus. Lone pairs are going to center around just 1 nucleus, and both electrons kind of choose that nucleus. The lone pairs are going to need more space than the bonding pairs, and they are going to kind of compress the angles between bonding pairs. So they're going to take up a lot more volume than you think they would if they were going to be atoms. Okay. So we've got a couple of factors that are going to affect our bond angles. And I'm not going to ask you to predict a specific bond angle, but what I might ask you to do is say, is this angle going to be what you predict? Is it going to be less than what you predict or more than what you predict? Right, what that ideal angle is. So here's an example where we've got carbon, it's double bonded to oxygen, and it's got 2 hydrogens over here. In theory, ideally, each of these angles will be 120 degrees in our trigonal planar geometry, right? So it should be 120 degrees between the hydrogen and the oxygen, and 120 degrees between the hydrogens themselves, right? That's ideally what happens. But this oxygen is going to have a larger electronegativity. It's got these lone pairs up here, right? A lot more of our electron density will be centered over this oxygen, right? And what we're going to see is a deviation from the ideal behavior where this angle here becomes bigger. These are taking up more space. It's kind of smooshing this hydrogen down. And the angle between the hydrogens gets compressed. Right? And so it's a little bit less, and these angles up here between the hydrogen and the oxygen are a little bit more. Lone pairs are going to repel bonding pairs more strongly than bonding pairs repel each other. So in tin chloride, we see the same sort of thing, where we've got this lone pair up here, and it's going to really bend those chlorines towards each other. Even though they don't want to be there next to each other, this guy is taking up way much more space. So all electron domains repel each other, but the repulsion between the domains depends on the types of domains involved. So a single bond is going to be less than a double bond, which is going to be less than a triple bond, which is going to be less than a lone pair, right? So your single bond are going to be your closest to ideal. Your lone pair is going to take up more volume, more volume than expected, with double bonds and triple bonds taking up increasing amounts relative to the single bond. Right, so if I look at some molecules that have lone pairs in them, like nitrogen or ammonia here has got this lone pair up here. We're expecting 109, but this repulsion is like, nah, get away from me. And so it pushes down on those hydrogens a little bit. In CH2O, right, we're going to have the lone pairs on this oxygen repel those hydrogens, bend those towards each other and away from those lone pairs. Here we've got sulfur, 1, 2, 3, 4, pentafluoride. We got a lone pair up here, right? And that's going to increase the angle it's going to make it less than 90 degrees, right? So it's going to be bent out of our axis. And these guys are going to be compressed with our bromine, 1, 2, 3, 4, pentafluoride here. Right? I've got this lone pair of electrons. These are not all flat anymore. They're bending out of plane up a little bit. And this guy is going to be unaffected. It will still be on that axis, but all of these guys that were in plane are now up out of plane. All right, so our lone pair is going to be bigger than our bonding pair, and which is going to be bigger than our bonding pair repulsion. When we put these into molecular shapes, we have some interesting stuff that comes up, including this concept of chirality. So here I've got a molecule, right? It's got yellow and 2 greens, right? 2 yellows and 2 greens, right? So this is carbon dichlorodifluoride. And this is also the same molecule, but the Lewis structures look different from each other, don't they? Here I've got the fluorines lined up with each other, and the chlorines lined up with each other. And in this Lewis structure, I've got the fluorines at 90 degrees from each other, and the chlorines at 90 degrees from each other. And in reality, they are the same molecule. Right? All this person did is they took their wrist and they twisted it, right? So that this guy rotates this way, and this guy rotates that way into the back, and then this guy rotates this way, right? So it's the same molecule, just twisted. And so sometimes our Lewis structures can be a little bit deceiving, right? So they are still the same molecule. Let's summarize what we have learned about our VSEPR. Okay, this table is incredibly handy. We will come back to it when we start talking about hybridization and hybrid orbitals. But all it does is it gives you a rundown on what all of our number of bonds that we've got, how many lone pairs we've got, how many charge clouds. Remember, the charge clouds are what determine the electron domain geometry, right? So this is determining our electron domain geometry. And what is our molecular geometry, whether we've got how many atoms versus how many lone pairs, right? So we've got trigonal planar or bent out of our trigonal planar electron domain geometry. Our tetrahedral electron domain geometry will give us molecules that are tetrahedral, trigonal planar, bent, and linear. There's like always that and linear that goes along with this. In our, if you got an electron domain geometry that's got 5 things, it'll be trigonal bipyramidal, seesaw-shaped, T-shaped, linear. If we've got octahedral, it'll be octahedral, square pyramidal, square planar, and then T-shaped and linear. The accuracy of the VSEPR model is that it aptly predicts the molecular structures of most molecules formed from non-metallic elements. It can be used to predict structures of molecules with hundreds of atoms, so you can carry that on from more than one atomic center to 2 atomic centers, and you can just keep going. However, it does fail to determine the molecular structure in certain instances. For example, phosphine, pH 3, and ammonia have similar Lewis structures, but very different bond angles, 94 degrees versus 107 degrees.